So this is example 23 in our vectors topic. We've been looking at intersections of lines, intersections of lines and planes, and even two planes. We know that if two planes intersect at all, then it's going to create, the solution is a line of intersection rather than a point of intersection. However, there's a few more options when we're dealing with three planes intersecting. And the three options that we've got, if three planes intersect, either they're going to intersect at one point, or along a particular line, or they're not going to intersect at all. With three possibilities. I've got an image here which you can have a look at, which there are 5 different images and they illustrate all 3 different possibilities. So there are several images here which indicate no solutions when we talk about intersection. Even though only one of them, clearly there's no intersections at all. But remember, when we're talking about 3 planes intersecting, we're talking about when they intersect all at the one time. So just to clarify, the first picture here, clearly the planes are parallel, so they don't intersect at all. There's no solutions. But also here, this is an image where 2 of the planes are parallel, so there are intersections that take place between 2 planes at any point, but the 3 planes never intersect at any one point, therefore there are no solutions. And also in this one down here, again, 2 planes intersect, but there's never a point where all 3 intersect. So all these 3 are examples where there are no solutions to our intersections. The second situation would be where the intersection forms a straight line, and that would be this one here, where they all intersect along a line. The solution, therefore, is the equation of a line. And the last possible scenario, it's certainly a rare, perhaps a rare occurrence, but here we have a situation where there is a unique solution, a point of intersection where all 3 planes intersect at one unique point in space. Okay, so that's the 3 possible outcomes of 3 planes intersecting. And the nice thing about it, it should tie into something that you already know, and that is the Gaussian elimination. Because when we solve a 3x3 system of equations, we're really just solving the equations of 3 planes. Okay, if you think about what we're trying to do with our augmented matrix, because if you remember that we're dealing with equations that look like that, that was our Gaussian elimination equations. These are all just equations of planes. So what you would find is that when you're doing a Gaussian elimination, and you might end up with a matrix like this. Let's get 0, 4, 8. If we have a matrix like this where we have an upper triangular matrix form, then clearly we can get a unique solutions for x, y, and z. Our solution is going to be 3 coordinate points in space, and that solution is our point of intersection. So the first scenario would be you can use Gaussian elimination. Unique solution is that point of intersection. Second scenario, intersection along a line. So that was the second picture that we saw. And what would happen here would be if you did your Gaussian elimination and you found that in actual fact there was redundancy. In other words, that the bottom line, once you did your elimination, you would find just a row of zeros. And we know from our Gaussian elimination that that means there are infinite number of solutions. And when that's the case, our solution is going to be the equation of a line. The infinite solutions are the infinite number of points along a line. What we're going to have to do, I've got an example just coming up here. What we're going to have to do is introduce a parameter and create the equation of that line. So that's the kind of one that's really interesting. The other one is slightly interesting, but we can't do anything with it, and that's the situation where we end up with inconsistency. So we end up with 0 values for x, y, and z, and we end up with some non-zero value in your constant matrix. In other words, 0z equals 4, which is an impossible solution, and therefore we say there are no solutions to that matrix, and therefore if there's no solutions to the matrix there, then there are no points of intersection at all, and what we've got is one of the images there in purple where there are no places where the planes all meet. Okay, so the first and the third scenarios there are manageable by just looking at Gaussian elimination. It's the second one here, the intersection along a line, that's kind of interesting because we haven't yet had a look at that. So here we've got example 23, find the equation of a plane. You find the equation, sorry, of the line of intersection of these three planes. What we can do is we can start off every time you would be looking at that, you would start off with some Gaussian elimination just to have a look at what's going on. So we've got 1, 1, negative 1, 0. Second equation 2, negative 1, 4, negative 3. And then we've got 1, 3, negative 5, and 2. So that's our augmented matrix here. We've got a 1 at the top left one. That's good. If not, we can switch the rows around. But because of that, we could do something like row 2 minus 2, row 1. And in the bottom one, we can just do row 3 minus row 1. And that will get us 0 values here and here. So that's the idea. So if we do 1, 1, negative 1, 0. And then for row 2, I've got 2 minus 2, 0. I've got negative 1 minus 2 is negative 3. And I've got 4, subtract negative 2, which is 6. And negative 3, subtract 0 is negative 3. And in row 3, I've got 1 subtract 1 is 0. I've got 3 subtract 1 is 2. Negative 5 subtract negative 1 is negative 4. And I've got 2 subtract 0 is 2. So looking at that, I've actually got 2 rows here where I've got a common factor. So I could actually, I'm going to divide that by 3. I'm going to divide this one by 2, just to kind of make the numbers a wee bit easier to work with. That will give me 0, negative 1, 2, and negative 1. And in row 3, 1, negative 2, and 1. And then what happens here, if to get the last row as 0, 0, so in other words, we want upper triangular matrix, I'm going to add row 2 and row 3, because I know that that's going to give me a 0. But if you notice, once we do that, we've got 0, negative 1, 2, and negative 1. When we add row 3 to row 2, all of the elements go to 0. In other words, I have a situation of redundancy. Redundancy exists. What does that mean? There are an infinite number of solutions. Now we've kind of left it at that when we're just doing our Gaussian elimination. But we can actually apply that into practice. In other words, that means that the three planes intersect along a line. So we can start to think, what's the actual equation of the line? Well, what we're going to do is introduce a parameter. Right, we've got some information in this last matrix down here that we're going to use. We'll start with this line here. So remember that we can give a parameter to t, say to x, y, or z in this kind of situation. It doesn't really matter, so I'm just going to say let z equal t. So if z is a parameter t, using that yellow equation there, we've got negative y plus 2z equals negative 1. And if I substitute that in there, and by rearranging it, we can say that 2t equals y minus 1, or y equals 2t plus 1. And what we're doing is we're basically building up our parametric equation. So we've got a z equation there, we've got our y equation, and we can use then the other equation from that last augmented matrix to then substitute in and find the x value. So we've got x plus y minus z equals 0. Substitute in x plus 2t plus 1 minus, that's just going to be t for z, equals 0. Tidy that up. And therefore x is negative t minus 1. So that's our x equation for the equation of the line. So that's me got my 3 different equations. So we can just summarize that and say that the equation of the line of intersection is x equals negative t minus 1, y equals 2t plus 1, and z equals t. Okay? Am I required to give it in a particular form? It's not. So I could leave it in parametric form. I could change it to symmetric form if required to. But that's the idea. Now, at advanced higher level, as far as I've never known there to be a question involving both Gaussian elimination and vector stuff. It's maybe regarded as too much in one question, but it's a nice way to see the two topics coming together, and for that reason I like the opportunity to investigate it, because it gives in a way a purpose to both of these topics. So there's no point in leaving them separate in my view. I think it's really good to investigate the two, bringing these two ideas together, because the Gaussian elimination is a kind of theoretical concept unless you apply it to something like vector maths. Okay, so hopefully that makes sense. You can try some others of that particular style.